Hello and welcome to Eng Phys 2P04 Lecture 25, Flexural Elasticity. Today we're going to look at the responses of beams to moments. When we've just got moments on the ends of beams like this, then the beam is in pure bending. So what's going to happen is the top part of the beam is going to get put into compression, the bottom part is going to get put into tension, and in general the beam is going to bend into an arc of a circle of radius rho. The inverse of radius is the curvature. So radius of curvature, rho, inverse of that is the curvature. And this is proportional to the moment, so more moment, more bending. Inversely proportional to the Young's modulus, because what's preventing the bending is this fighting back from the compression on the top and the tension on the bottom of the beam. And the second moment of area of the beam about its cross section. So the cross sections are kind of slices through the beam like this. If you imagine one is in the vertical direction and the other dimension is into the page. Those are the two dimensions. So it's not this way. It's a cross section if we slice through the beam like that. And so the second moment of area about the bending axis of the cross section is, for a given cross section, the bending axis is in and out of the page. So if you picture the y direction is up, x is this way, and z is out of the page, then we're looking at the moments about the z axes of those cross sections. Now, we want to be finding the second moment of area about the center of that. So the distance away from the z-axis is the y-coordinate. The y location of the centroid in that axis is the integral of y dA over a, and the second moment of area is the integral of the distance from that center y value with respect to a. So the integral of that thing squared over that entire area. Collectively, E times I is called the flexural rigidity of the beam and kind of tells you how stiff it is in response to bending. So the bending is also known as flexion, and flexural rigidity is a resistance to bending. It's a stiffness for bending. Now, once the beam starts bending, its cross sections that were originally in the YZ plane kind of rotate. So you see this cross section here in the center is still in the YZ plane. But this one up here is well, it's in the Z, and then the other dimension is kind of a little bit of Y and a little bit of X. It's kind of rotated about Z because the moments here. So what direction are the moments? The moments are about the Z-axis, right? And so this is rotating this cross-sectional plane about the Z-axis when the moments are successful. Now, because of that, it's useful to distinguish between the original coordinates of the beam and the coordinates after it's deformed. As long as we're talking about the original coordinates, then any of these cross sections are still in the YZ plane because that's referring to their original coordinates. All right, the integral used to locate the y coordinates, by the way, of the centroid, this is called the first moment of area about the z-axis in the top here. And so you take the first moment of area and you divide it by the area, and that tells you the location of the centroid. You may remember this from first year math. The axis that runs through the centroid of each cross section, so you've got a cross section here, there's a centroid, cross section here, centroid, cross section here, centroid. If you take all of those centroids and connect them up and form an axis, then that axis is the location where there's no compression and no tension. So the points above that after bending will have compressed. The points below that will have tensed. So we've got no deformation on that axis. It's just neutral. It hasn't changed. And so we'll call it the neutral axis. All right, let's prove this formula that we were just using up here. The curvature is equal to m over EI. The way that we're going to do this is by thinking about what the strain is at every point inside the beam. To figure out what the strain is, we're going to need to know what its new length is. Its original length is equal to rho times phi, where phi is the angle that we've bent into here. because the rho is the radius of curvature of the neutral axis, and the neutral axis hasn't changed length, it's still at its original length of rho phi. We can use the same arc length formula to find the new length of any point by recognizing that the radius of curvature of a point up here at, let's say, distance y from the neutral axis is rho minus y. So as y gets larger, then the radius gets smaller, proportional to y, right? So the length of the part at the top, or at any point, would be rho minus y all times phi, which means the strain is rho minus y phi minus rho phi, all divided by rho phi. So the strain is negative y over rho. Stress is just the Young's modulus times the strain, and the force is the stress times the area. So the moment would be negative y times this little bit of force integrated over the whole thing. Why negative y? Because the force, by our positive sign convention, up here at positive y, the force is going out if it's positive. So positive force times positive y would make a moment in the other direction. So the moment in the direction we're showing about z is actually just positive force times negative the y coordinate. Okay, so then the moment is the integral of negative y df, substituting in the df that we found, and then looking at this, hey, that integral of y squared dA, that's just the second moment of area about the neutral axis. So we come up with the result that we had earlier. The moment is equal to EI over rho. All right, an example where we get to use all of these things we were talking about. We've got a rectangular beam with Young's modulus E, length L, thickness H, width B, and we're going to say the beam extends from 0, 0, 0 to LHB. Find, for bending in response to moments in the Z direction, find the beam's cross-sectional area, first moment of area of its YZ cross-section about Z, YZ centroid, second moment of area of its YZ cross-section about the Z parallel axis through the centroid, which is the I that you would use to calculate flexural rigidity for this type of bending, the flexural rigidity in response to the bending, curvature, radius of curvature, bending angle, and maximum tensile and compressive stress. To do this last one, you're going to have to consider the derivation, so the proof that we did up here. The rest of them, you don't actually need the proof, although it's good to understand the proof. Okay, cross-sectional area, you just multiply the width and the thickness. First moment of area of its cross-section about Z, considering the coordinate system, Z equals 0. So the Z-axis is at y equals 0. We're going to need that, so we integrate y dA from the y bounds would be 0 to h, and we get bh squared over 2. YZ centroid would have the y coordinate of its mz over a, so that turns out to be h over 2. Not surprising, it's just halfway up in y. Similarly, in z, it's halfway through the extent in z. Second moment of area of its YZ cross-section about the Z parallel axis through the centroid. This is the one that you would use for bending. So if the beam is looking like this, and we've got X here, Y up, and Z out of the page, the Z axis through the centroid of the cross-section would be the one in the middle, the one that's at Y bar. Okay, so that's IZZ is the integral of Y minus Y bar all squared. Substituting in the Y bar that we calculated, and then saying that in the width direction, we can just do that integral. It's an iterated integral. We don't need to, there's nothing changing inside with the width for this beam because it has a rectangular cross-section. So we'll get that it turns out to be bh cubed over 12. Flexural rigidity is just E times this I. Curvature, from our formula above, is m over EI. Radius of curvature is 1 over the curvature, so just invert that one. Bending angle phi is the length divided by the radius of curvature. This is using the arc length formula, or in other words, length times the curvature. And the stress. So as part of this derivation here, we figured out that the stress was Young's modulus times the position relative to the neutral axis. In this example, we defined the neutral axis as y equals 0, divided by rho. So now, to find the stress, we actually need just remember that the y's for the stress formula are relative to the neutral axis. So the max compressive stress would be the distance from the center to the top of the beam, so h over 2. And the tensile one would be at the bottom of the beam, negative h over 2. If m turns out to be negative, then actually this one here is the compressive stress and this one is the tensile stress. So that makes sense. If the moment is actually in the other direction and we're bending down, which we would define as negative radius, then we get tensile at the top and compression at the bottom. So to level up your physics intuition, look at these equations and consider how things affect the answer. So for instance, the bending angle here is proportional to the moment. More moment means more bending. More length means more bending. More width of the beam means less bending, linearly proportional to the width, because that same moment is kind of distributed over a bigger width of the beam. The biggest effect on bending, though, is the thickness. Thickness affects the rigidity of the beam according to thickness cubed. So as things get a lot thinner, then they become much, much easier to bend. This is probably the #1 reason that paper is so easy to bend, is because it's so thin. If you pick up a phone book and imagine you were to take all of the pages of the phone book and stop them from being able to slide over each other, so in certain directions that's true, then it's really actually quite difficult to bend compared to how easy it is to bend paper. Okay, check your understanding. This is an I-beam. It's much more difficult to machine than just a rectangular beam. We've got to carve out these interior sides, maybe use some molding to make this shape. But it's far more common to see this in building construction. First question, why is this called an I-beam? And what advantages does this have over a rectangular beam? Well, it's called an I-beam because that's the shape of its cross-section. Do you see the I? There it is. And the advantage it has is that for a given area, so the cross-section has a pretty small area, but a lot of its area is very far away from the center point. So for bending about this axis or about this axis, we've got a lot of the area far away from the center. That means that it's going to have a comparatively large second moment of area in either of those dimensions compared to its actual area. And so a high flexural rigidity for a given area and a high strength to weight ratio. It's going to resist bending a lot for a given weight. It's not going to resist it as much as if this was all filled in. But if you were to fill that all in, then the beam would be way, way heavier. Let's compare everything that we've dealt with so far in terms of our different Hooke's laws. So we had normal stress is related to the normal force divided by the area, giving us a strain in terms of the normal length change, so the axial length change in the same direction as the force per unit length. And our Hooke's law was sigma is equal to Young's modulus times the axial strain. Then we talked about shear, where we said now the force is parallel to the plane, divided by the area, that gives us a shear stress, and shear strain, where the relation between the two is the shear modulus. Then we talked about torsion, where we said the torque divided by the torsion constant is kind of like the stress, and this gives us a strain, which is an angle of rotation per unit length. The relation between the two, again, being the shear modulus. And now we've talked about flexion or bending. The stress is kind of like the moment distributed over that surface, so maybe moment divided by the second moment of area. The strain you could call the curvature that results, which we'll see shortly is proportional to the second derivative of the transverse displacement with respect to length. And the Hooke's law for that would be that the stress, the moment over I, is equal to E times C. So what's the difference between torsion and flexion? I mean, is flexion just torsion again? Well, torsion is really a shear phenomenon. You can see because it's using the shear modulus as a hint. And flexion is actually an axial phenomenon. So here's a picture I found on the French Wikipedia. So it's using slightly different symbols for some things. If we apply a force like this, then we're putting the beam into flexion, so it's gonna bend, and you see that the deformation is all along the axial length of the beam. Now for torsion, it's applied parallel to the face rather than perpendicular to the cross section, and that's what's giving us a torsional deformation. All right. In general, what if a beam has more than one layer throughout its thickness, and then we're going to try to bend it about an axis perpendicular to the plane that we're showing on the screen here. So we're going to be taking the cross section and then putting it into flexion. An axis is in the plane of the cross section for usual flexion, but it's perpendicular to the screen that we're showing here. Then which Young's modulus do we use? Well, we've got a different Young's modulus for all these different layers inside the beam, so we need a different formula to calculate this. The density of this combined beam is just the weighted average of the density, where the weighting is area. And you could say that the Young's modulus for extension is a weighted average of the individual Young's moduli of the layers, weighted by the area. And these are great if you wanted to calculate the elongation in response to a force, or the total mass of the thing. But the calculations for flexure are a little bit more complicated. One quick way to calculate the new flexural rigidity of the beam is by using the parallel axis theorem and this formula here, where now the centroid is located at something similar to the previous centroid, except now we're weighting all of the layers by their Young's moduli. And you take the individual centroids of each of the layers, yi, and then add all of those up, multiplied by the area of each layer and its Young's modulus, and then divide by the sum of the areas multiplied by Young's moduli for each of the layers. And that'll give you the new centroid location. And then if you calculate the second moment of area, or the flexural rigidity EI of each layer individually acting about its own centroid, you can find the combination centroid by adding up EI and then AE, the distance away from the total beam's centroid, squared. This is an application of the parallel axis theorem. If you don't like the parallel axis theorem, that's okay. You can just use the integral version of this formula instead, and say that the centroid of the whole thing is the same calculation as the previous centroid, except now we're going to be weighting it by Young's modulus, which could change. And the flexural rigidity is similarly weighted by Young's modulus. All right, we're going to use an example to show that this actually gives the same result as this formula. Flexure of a bimetallic strip. A bimetallic strip is 30 centimeters long, 3 centimeters wide, and 1 millimeter thick, and is made of 2 layers, tungsten and aluminum. If the aluminum layer is 70% of the thickness, calculate the linear density, mass, combined axial Young's modulus, and flexural rigidity of the strip. Then calculate the curvature, radius of curvature, and arc angle that results from a bending moment of 1 Newton meter. So the bending moment is in the width direction, so it's going to be using the thickness here as kind of our h in this formula, the thickness in this formula, and the width as the b for the calculation earlier. So we've got 30 centimeters long, 1 millimeter thick, and then 3 centimeters wide in and out of the page, and we're bending about the easiest to bend direction, the one that uses this 1 millimeter thick as the thickness. Okay, cross-sectional area, 3 times 1. The linear mass density, we would average the densities, weighted by their individual areas. The mass is just the linear mass density times the length. Combined axial Young's modulus, this would be useful to figure out how this would respond to an axial stress. The AE centroid and flexural rigidity using the formula above. Therefore, in response to the moment of 1 Newton meter, we find a radius of curvature of 0.35 meters, curvature of 2.85 per meter, and an angle for this 30 centimeter beam of 49 degrees. And we can check this using our integral formulas, say by defining a piecewise function in Maple, calculating the location of the centroid by the integral of the position weighted by the Young's modulus, divided by the integral of the Young's modulus. And then EI is the integral of the position relative to the centroid squared, weighted by the Young's modulus. And that's it. Same results as above. Okay, now consider some general loading of a beam here. We've got a distributed load on the top here, and some supports. From our static equilibrium material that we knew earlier, we could figure out what the support reactions are, and we can find the internal shear force and bending moment and draw a diagram of that. Now that we know the deformation in response to bending moments, we can find the deformation of this beam. To make it easy on ourselves, we're going to be assuming that the bending moment deformation is small, in which case the curvature is equal to the second derivative of the transverse displacement with respect to x. So this is the assumption that results by saying that the curvature is so small that it just gives us a transverse displacement. The longitudinal displacement is 0. Now, if this is bending into a circle that's kind of a 90-degree arc, then that's going to be broken. This only applies for very small curvatures. If we have larger curvatures, we can still solve these types of problems, but we have to be careful about how things are applied. So as the beam starts bending, then is this distributed load still in the down direction, or are we applying it in the perpendicular direction to the beam, so it becomes non-transverse if the beam bends a lot? For now, we're going to ignore all of that and just say, well, if the deformation is small, then the cross-sections stay in the xy plane, and we can say that the curvature is given by the second derivative of the vertical displacement with respect to the horizontal distance. Okay, anyway, solving the static equilibrium conditions give us the reaction force at each side is L_P0 divided by 2, and we can find the internal shear force would be changing with the x displacement. Shear force drawn using this sign convention. Internal bending moment similarly. And we could also have found the internal bending moment just by integrating the shear force, because there's no bending moment here, so we don't need to add any constant to that integral. Now we know how the bending moment leads to displacement from our calculations in this section. So by substituting in m is EI second derivative of v with respect to x squared, we can calculate what the deformation would be as a function of length. So by integrating that twice, we come up with our transverse displacement as a function of position along the beam as the transverse displacement at 0 plus its slope at 0 times x plus 1 over EI and this term. Now, if we know that at 0 and at L, the transverse displacement is equal to 0, so we say that because of the supports, it can't move vertically here or here, then we can substitute these conditions, these boundary conditions, into the differential equation's solution to solve for what these two constants are and come up with what the entire transverse displacement is at each point along the beam. Let's put some numbers to this. So suppose the beam is 1 meter long, 10 centimeters thick, and 20 centimeters wide, and E is 100 gigapascals, and the distributed force has a magnitude of 1 kilonewton per meter. Then the transverse displacement versus x is as plotted here, going down to about 7.5 in the halfway along the beam location. So we do have an angle at each of the edges because we're not fixing us to not have an angle. So you can picture if we put a distributed load here, probably the beam would bend like so. Okay, a little bit more general than this approach is to differentiate the moment equation twice and arrive at what's called the beam equation. So if we take our moment equation here, we differentiate it once to get the shear, and differentiate that again. The derivative of the shear is just equal to any kind of distributed load that we have on the beam. And we know that that's now equal to EI, the fourth derivative of the transverse displacement with respect to x. This fourth order differential equation in position we can solve by integrating 4 times to come up with these 4 constants. Now to determine the constants, we just need to know what our boundary conditions are. And what conditions you have at each boundary depends on what type of boundary it is. If it's a free boundary, then there can't be any shear force or moment applied there. The shear force goes like the third derivative of position. The moment goes like the second derivative. But if it's free, then we can't say anything about what the position is or what the angle is. On the other hand, if it's clamped, then we have the opposite. So there's no angle at the edge, and there's no displacement at the edge. But that clamped boundary will apply whatever shear force and bending moment are necessary to maintain that. A pivot joint, like the ones shown above, have they apply whatever shear force is necessary to stop position, but they can't apply moment and consequently can't constrain the angle. The opposite of that would be a vertical slider. So this is one where it's kind of clamped, but then can slide up and down. So that means that it can't apply a shear force, but it'll apply whatever bending moment is necessary to stop an angle. If we apply the boundary conditions that we have for this problem, so pivot joint boundary conditions at each end, which say no moment applied and no displacement, then we can solve all of this and come up with the position the same as above. Now, if you were really following along with that last example, you may notice that we said, well, okay, we know what the moment causes in terms of deformation. So we said, well, the bending moment that's applied here, we know causes a deformation due to curvature. And so we can find, just using that deformation, what the deformation of the entire beam is. But you may have thought, well, hang on a second, doesn't the shear force cause a deformation as well? It should cause a shear strain, and that's kind of like, that's like an angle with respect to position, so shouldn't that be changing the position as well? And yeah, it does, but it's negligible for this type of dimension. So let's calculate the shear force. It's the shear stress, the shear stress is the shear force divided by the area. And for our directions on the x face in the y direction, which would be up, we defined the shear force as going down for positive, so we just have a negative sign showing up there. And this tells us what approximately the displacement due to shear is at, say, the end of a beam. Let's imagine it's a cantilever beam now. For simple loading at each end, we're going to have moment that's maybe not exactly equal to shear force times the times the length, but on the same order of magnitude as this, depending on the type of loading that you've got. So the shear displacement, substituting in the moment so that we can compare the two, is going to be on the order of moment times 2, 1 plus nu over E, where we've also substituted in what shear modulus is in terms of Young's modulus. Okay, now we also said that the bending displacement goes like C L squared over 2 if we're using this small deformation approximation. Comparing the two, you can see the bending displacement is on the order of negative 6 over 1 plus nu L over H all squared times the shear displacement, where we're being a little bit sloppy with negative signs, just to give an idea of what the deformation is. Okay. We'll be a little bit more rigorous in some examples in the future once we've got an actual decision on what kind of loading we're talking about. Still, this does establish the idea that the bending deformation scales with length over h squared compared to the shear deformation. So if you've got a beam which is much longer than it is thick, then for most loading, the flexion deformation is going to dominate over the shear deformation. There's an example which is going to look at this in detail in the sample assignment. All right, next example, we're going to take the same problem that we solved up here, and we're going to try and solve it for a cantilever boundary condition instead. So that means the left end is fixed and the right end is free. Give it a shot to solve this on your own. It'll be a good opportunity to sub into the last example and see if you can follow along with how things were done. The result is we just have these boundary conditions instead, so you could sub right into Maple and solve that if you like. We'll find that the tip displacement is negative 75 microns. So by having a cantilever boundary condition, we get quite a lot more deformation at the other end. After all of that, you'll be pleased to hear that solving it with FlexPDE is surprisingly easy. So what modifications do we have to make to FlexPDE to let it solve bending problems? Answer: nothing. Internally, bending is not doing anything different than the stress and strain that we were already accounting for with our equations. So all you need to do is apply the different boundary conditions. Here's a cantilever. We've got nothing constrained anywhere except the left end is fixed, and we've got a distributed load across the top. Doing this, you find the same kind of deformation that we got with Maple. So the value at the end is about 75 microns displaced down. Now, the analytical work used a small angle approximation and ignored the shear deformation, but nevertheless gave us a pretty close answer. FlexPDE doesn't make these assumptions, but it does have its own problems, like the limited grid size in the student version. To see some of the effective shear strain, you can artificially reduce or increase the shear modulus. Reducing it by a factor of 10 gives us about maybe a 10% increase in the deformation at the end. So you can see that the shear deformation was about 1/100th of the bending deformation. That kind of makes sense from what we calculated in terms of the shear deformation here. Because the beam is 10 times as long as it is thick in this direction, as it in this problem rather, then we expect that the bending deformation is going to be about 10 squared times as much as the shear deformation. Now, you can also increase the shear modulus by a factor of 10 to completely to reduce the shear and see if it was making any kind of an effect. And yes, it was having some effect on things. At the tip now we have negative 7.47 instead of negative 7.54. So the shear was responsible for some of the deformation, and our analytical work ignores this, but it's not a very big deal if the beam is a lot longer than it is thick.